Alright, welcome back everybody, and today I'm going to go over the solutions to the 2020 Specialist Maths Exam 1. So I just sat this exam this morning. It was quite an interesting exam. It wasn't as bad as I expected. I was expecting much worse after methods for the past 2 days. But yeah, there was a lot of integration on this exam, which I was very happy with because I love doing my integrals. But yeah. Overall, it was a pretty good exam, made a couple of careless mistakes, but yeah, we'll get into what those were later on. But let's just take a look at the first question right here. So the first question, we're given this system, we have this 2 kilogram block, and it's on a smooth surface, so no friction whatsoever. And we have 2 forces acting on it. We have a 10 Newton force acting 60 degrees up from the horizontal, and this other 5 Newton force acting on the other way. And the first question, part A, asks us to find the normal force on this thing. Well, we know there's this weight force going down, which is 2G. And if we kind of ignore these 2 forces, well then the normal force would just be 2G. But since we also have these additional forces added on going up this way, then the normal force is kind of reduced a little bit. So first of all, we have this weight force 2G, and then the normal force is reduced a little bit, first by this other force which is going vertically up, and this other force over here, and we have to find those 2 magnitudes. And since this is the opposite side to this angle, we're going to be using sine, because opposite over hypotenuse. So this is 10 times the sine of 60 degrees, so sine of 60, and over here we're going to have 5 times the sine of 30 degrees. So we're going to subtract off each of these 2 forces. So 10 sine of 60 is root 3 over 2. So if you multiply that by 10, we're going to get 5 times root 3. Then over here, we're going to subtract off this other vertical force. Sine of 30 is a half, so 5 over 2. And that's the normal force. And next we have to find the acceleration. Well, this block is going to be moving side to side, so let's try to find these horizontal forces. So this is on the adjacent side, so let's use cosine. So this is going to be 10 times the cosine of 60, and over here we're going to have 5 times the cosine of 30 degrees. So you can guess either direction, it's going to work out the same way in the end anyways. Let's just guess that the block is moving to the right, so we're going to have net force is equal to 10 times the cosine of 60, but cosine of 60 is exactly 1/2, so in fact this is just 5, and then minus, now 5 times cosine of 30, that's going to give us 5 root 3 over 2. And now this is find the acceleration. So force, net force, is equal to mass times acceleration, but mass is 2 kilograms, so we have 2a. So to find a, we divide both sides by 2. Let's kind of turn this 5 into a 10 over 2, so we can combine it with this fraction. And we're going to find the a. Once we divide by 2, it's going to give us 10 minus 5 root 3 over 4, like so. And now we have to find the distance covered in the first 4 seconds. Let's see. We're going to be using a bit of suvat. So S equals ut plus 1/2 at squared. That's one of the suvat equations. Because we know what acceleration is, we actually know what initial velocity is. This block starts from rest, it says in the question. So if this starts from rest, this is 0. And we know what the time is. It's the first 4 seconds. So S is equal to 1/2 times the acceleration, which is 10 minus 5 root 3 over 4, and then time squared, which is 4 squared. Now, one of these factors of 4 can cancel out with 4 down here, and we have 4 divided by 2, which is 2. So we have in the end S is equal to, now 2 times whatever's left in the numerator is 20 minus 10 root 3 meters. For the next question, we're asked to evaluate this integral. So the first thing I did was I let u be equal to the inside of this square root to kind of simplify it down a little bit. So we let u be equal to 1 minus x, which means du is equal to minus dx, which means that dx is equal to minus du. So we're going to be subbing in this expression for dx later on. And let's take care of the bounds as well. So notice u at -1. Well, if you plug negative ones into here, you're going to get 1 minus -1, which is 2. And u at 0, well, plugging in 0 into this x, we're going to get 1 minus 0, which is 1. And now this integral turns into the integral. Now minus 1 turns into 2, so we have a 2 to 1 of 1 plus. Now let's figure out what x is. If you rearrange this equation a little bit, you get x is equal to 1 minus u. So 1 minus u, like so. This is divided by the square root of u, because 1 minus x is u, and dx turns into minus du. Now we can use this negative in this du to flip the integral around, because this is kind of in a weird orientation. So we have the integral from 1 to 2 now, now we have 2 minus u, but that's the same thing as 2 over the square root of u, minus u over the square root of u du. But let's split this integral up, so this is 2 times the integral from 1 to 2. 1 over square root of u is the same as u to the minus 1/2 du, minus, now we have the integral from 1 to 2. U over square root of u is just square root of u, which is u to the 1/2 du. And now we're left with 2. And evaluating this antiderivative, that's not too hard to do. We just add 1 to the exponent, so that's going to be u to the 1/2, and divide by 1/2, which is the same as multiplying by 2. Then we're going from 1 to 2, minus, now anti-differentiating this, we should get u, adding 1 to the power, that's 3/2, dividing by 3/2, it's the same as multiplying by 2/3. And we're going from 1 to 2. And now let's pull these constants out, because they're in the way a little bit. So 2 times 2, that's 4. And then plugging in 2 into this square root of u, that's square root of 2. Plugging 1 into here, that's minus 1, because that's the second part of integration. And then we have minus, now we have 2/3. Plugging 2 into here, well, if you take 2 raised to the 3/2, you're going to get 2 root 2, and then plugging 1 into here, well, 1 to anything is just 1, so subtract 1, and now this is going to give us 4 root 2 minus 4 minus, now expanding this out, that's 4/3 root 2, and then plus 2/3. Now what I want to do is simplify this down a little bit, because the question does ask us to put it into the form a root b plus c, where a, b, and c are real numbers. So notice we have thirds right here, so let's turn this 4 into 12 over 3, 12/3, and same over here, 12/3. So now we can combine the fractions a little bit, so 12/3 root 2 minus 4/3 root 2, that's going to give us 8/3 root 2, and then minus 12/3 plus 2/3, that's minus 10/3, and that's the final answer. For the next question, we're asked to solve this inequality. This is question 3. So I used a graphical approach in this exam, so I graphed out each of these functions. So first of all, let's take a look at the right hand side. Notice 1 over absolute value of x minus 4. That's the same thing as the absolute value of 1 over x minus 4. But we know how to graph this inside. If we chuck this onto a graph, we have an asymptote at x equals 4. And well, if you graph it out, you're going to get a hyperbola like that. But since this is the absolute value, we're going to reflect that negative region up to the positive region like so. And then we have 3 minus x. So we have a y-intercept at 3, and we have a slope of -1 going down like so. So we're asked to find where 3 minus x, so this is 3 minus x, is greater than the absolute value of 1 over x minus 4, like so. And that happens only on this left-hand region, because everywhere to the right, this is always greater than 3 minus x. So we're only concerned about this left-hand region. So we can kind of reduce this question down into finding this point of intersection between the two graphs, because if we can find this, then the interval is pretty easy to state. It's just from minus infinity to whatever this is right here. So notice this is on the negative branch of this inside of the absolute value. So we can solve for where 3 minus x is equal to minus 1 over x minus 4. But let's bring this negative onto the other side. So x minus 3 is now equal to 1 over x minus 4. And now, multiplying both sides by this factor, we're going to get x minus 3 times x minus 4 is equal to 1. Expanding it out, x squared minus 7x plus 12 is equal to 1. And we get x squared minus 7x plus 11 is equal to 0. Okay, very nice. And now this can't really factor nicely, so let's use the quadratic formula. So x is equal to minus b, which is 7, plus or minus the square root of b squared, which is 49, minus 4ac. So 4a is 1, and c is 11, like so. This is divided by 2, so 2a. Let's go over here now. So now we have that x is equal to, we have 7, 4 times 1 times 11, that's 44. 49 minus 44, that's 5. So 7 plus or minus the square root of 5 over 2. And notice, if you take the positive branch, that's going to be the intersection point if you continue this minus 1 over x minus 4 down here. But that doesn't exist because we're only having the positive values. So we have to take the negative branch. So x is equal to 7 minus root 5 over 2. So we found this intersection point. It's 7 minus root 5 over 2. And now where is 3 minus x greater than this absolute value thing? Well, x is on the interval minus infinity. And since this is strictly greater than, we're going up to 7 minus root 5 over 2, non-inclusive of the endpoint, and that's the answer. I just realized that was question 4 on the exam, not question 3. Question 3 asks us to find the cube root of the complex number 1 over the square root of 2 minus 1 over the square root of 2i, like so. And first thing to notice that is that this complex number actually lies on a unit circle, and since we have a negative right here, you can kind of deduce that this is the same thing as, well, I use the exponential form for complex numbers in this exam, so e to the minus I pi over 4. But in this video, just so everyone's familiar with the notation, well, I'm going to be using the cis notation, so cis of minus pi over 4, like so. Okay, so we have to solve where z cubed is equal to cis of minus pi over 4. We have to solve for z. So the way to do that, you take z cubed, and this is equal to cis of minus pi over 4. But notice, the complex number won't change at all if you just add on 2 pi k, where k is an integer. So you're just rotating another revolution around. And since this is a third power, you consider the k values 0, 1, 2, all the way up to 3 minus 1. So we stop at 3 minus 1, which is 2. So we only consider these 3 k values, because if you keep going, then you're just repeating your solutions. So now we can take the cube root on both sides. So if you take the cube root, you're dividing the argument by 3. So z is equal to cis of minus pi over 12 plus the 2 pi k over 3. And just to make things easier later on, let's combine these two fractions together. So this is cis of, well, we want to multiply top and bottom here by 4. So this is the same as 8 pi k over 12. So we have minus pi plus 8 pi k over 12. And now it's just a matter of subbing in each of these k values, because we basically already have a general solution for z. So at k equals 0, well, if this is k equals 0, then this 8 pi k will disappear, leaving us with cis of minus pi over 12. as one solution. If you let k be equal to 1, then we're going to have minus pi plus 8 pi, which is 7 pi. So cis of 7 pi over 12. And for k equals 2, well, you're going to have, let's see, 16 pi minus pi, which is 15 pi over 12. So 15 pi over 12, but the question also states that the arguments must be in the principal argument. So this is definitely outside of the domain minus pi to pi. So if you visualize this on the complex plane, if you have 15 pi over 12, then you're going 12 pi over 12 plus an extra 3 pi over 12, which is exactly pi quarters. But this complex number you land on, you get there the same way by just traversing the angle in the other way by 3 pi over 4 radians. So in fact, when k equals 2, you get a cis of minus 3 pi over 4, and those are your solutions for z. For the next question, we're given two vectors a and b, and we have to find the value of m, so find the m. And the question also states that m is an integer, so find m that's in the integers, such that the vector resolute of a in the direction of b is given by this other vector. So the first step to do is to, well, write down the formula for the vector resolute of a in the direction of b. So I just used the form a dot b over b dot b times b, like so. It's quite easy to remember for me. And well, the first thing to do up here is to compute a dot b, or a dot b, well, let's take a look. So 2 times 1, which is 2, minus 3 times m, which is minus 3m, and 1 times minus 1, which is minus 1. This is divided by b dot b, so we take 1 times 1, which is 1, m times m, which is m squared, and then minus 1 times minus 1, which is just 1. And this is times b, but b is the vector I plus mj minus k, like so. But notice one cool thing. The vector right here that they give you is the same thing as b. So in fact, if this vector and this vector is the same, remember this is the vector for the vector resolute of a in the direction of b, and we have b over here as well as b over here, that means these scalar multiples in front of the vectors must be the same. So in fact now, let's see, 2 minus 1, that's just 1, then minus 3m over 1 plus, or 2 plus m squared rather, is now equal to minus 11 over 18, and this is what we have to solve. And to solve this, let's cross multiply a little bit. So we have 18, 1 minus 3m is equal to minus 11, 2 plus m squared. And we get 18 minus 54m is equal to minus 22 minus 11m squared. And now let's rearrange things a little bit. So we get 11m squared if we bring this over, minus 54m. Now we have 18. If we add 22 on both sides, 18 plus 22 is 40. And this is equal to 0. And now we have to solve this quadratic. I actually didn't see this on the actual exam. There's a nice factorization you can use. I think it was like 11m plus 10. And then you also have, let me check my notes. You should also get m minus 4 on this other factor. But I didn't see this, so I just brute forced through the quadratic formula. So let's go through the quadratic formula method, which is the method I used. So we have minus b, so b is minus 54, so minus b is 54, plus or minus, this is m by the way, so m is equal to 54 plus or minus the square root of 54 squared minus 4, a is 11, and c is 40. And this is divided by 2a, which is 22. And now let's see, what can we do? 54 squared, if we compute this using the multiplication algorithm, well, we have 16, 5 times 4 is 20, plus 1 is 21, then 20 again, 25 plus 2 is 27, so we get 6, 1, 9, 2. And then 4 times 11 times 40, well 4 times 11 is 44. 40, let's just consider 4 for now, so 16, and that should give us 17. And since we have 40, let's add an extra 0. So we have 54 squared, which is this thing, minus this other junk, which is 1760. So let's take 2916 minus 1760. That's going to give us 6. Let's borrow a 1 from this 9. So we have 11. So 11 minus 6 is 5. 8 minus 7 is 1. 2 minus 1 is 1. We get 1156. So m is equal to now, we can split this fraction up a little bit. 54 divided by 22, that's the same thing as 27 over 11, plus or minus 1 over 22, square root. Now the inside we're left with 1156. And now I had a feeling that 4 would fit into this nicely because 4 divides 56 nicely. So if we divide 1156 by 4, which is a square number, well, 2 times 4 goes into 11, leaving us with 3. Bring down the 5, let's see, we have 8, so 8 times 4 is 32, remainder 3, and then we got 289. So this is equal to 27 over 11 plus or minus 1 over 22. We have 4 times 289 in here, but the square root of 4 is 2, and that 2 can cancel out with this 22 to become 1 over 11, square root of 289. And this took a little bit of thinking, but this square root of 289, this is 27. So we have 27 over 11 plus or minus square root of 289, that turns out to be 17. So plus or minus 17 over 11. So if you take a look, if you take the negative case, 27 minus 17, that's 10 over 11. So m is either equal to this, or m is either equal to 27 plus 17, that's 44. 44 over 11, which is 4. But the question states that m is an integer, so we're going to reject this solution, and finally m is equal to 4. And the next part of this question asks us to find the perpendicular component of A in the direction of B. So if you imagine this is your A over here, and this is your B, what we found was the vector resolute of A in the direction of B, and now the second part of this question asks us to find this other vector. So let's call the vector resolute, I don't know, W for example, and we'll call this perpendicular component U. So how can we find our U? Well, we want to start here and end here. Well, first of all, we can traverse W in the other direction and then add A. So minus W plus A, so that's A minus W. So we're going to take our A, which is 2I minus 3J plus K, and then we're going to subtract off W, and since there's a negative right here, that's the same as adding 11/18. This is the first vector, adding 11/18 I plus 4J minus K. And now let's see, we have an 18 on the denominator, so let's try to get 18s everywhere in the denominator. So first of all, over here, 2 is the exact same thing as 36 over 18. 3 is the same thing as 54 over 18J, and then K, well, that's just 18 over 18K hat, like so. And we have 11 over 18I plus, now 4 times 11 is 44 over 18, J minus 11 over 18K, like so. Okay, now we just add each of these components together. So 36 plus 11, that's 47 over 18I, minus 54 plus 44, let's see, that should give you minus 10, but minus 10 over 18 is the same thing as minus 5 over 9J. Yep, that should be right. And then 18 minus 11, that's exactly 7, so we have plus 7 over 18 in K hat, and that's the answer. So the next question, question 6, we're given this function f of x is equal to the inverse tangent of 3x minus 6 plus pi, and the first part of this question asks us to show that f prime of x is equal to some expression. So let's just evaluate f prime. So derivative of arctangent, that's 1 over the inside squared plus 1 times the derivative of the inside, which is just 3. And then the derivative of pi is 0. And expanding this bracket out, we get 3 over 9x squared. 3 times 6 is 18. 18 times 2 is 36. So 36x minus 36x. And then 6 times 6, that's 36, plus 1 is 37. And that's the exact expression we had to show. And for part B of this question, we had to show that x equals 2 is an inflection point on our graph f of x. And for one reason or another, I didn't use the double diff method. I used some derivative test, which isn't valid until you do the double diff test. So let's find the double derivative. It was actually pretty stupid of me not to think of this, probably because I was in a rush and this just skipped past my mind. But double derivative, let's see, to evaluate this derivative, what we do, we have 3 over some function of x, so the 3 remains, and then the function of x gets squared, so 9x squared minus 36x plus 37 squared, but because of the power rule we also introduce a negative, and then we have to differentiate the inside, which is 18x minus 36, and then we have to solve for where the double derivative is equal to 0, and assuming this denominator isn't 0, and well, minus 3 isn't 0, we can cancel this out with a 0, and we're left to solve 18x minus 36 is equal to 0, which means that x equals 2. So if you plug x equals 2 into the double derivative, you get 0. So there could be a possible inflection point. And to go further, you can test on both sides. So f prime of 2, I think that was 3. If you plug 1 in, you get something like 3/10. And same thing for f prime of 3, you also get 3/10. And since these values are less than 3 on either side, then x equals 2 is indeed an inflection point. And final part of this question, it was pretty easy. We just had to sketch this function. So we're given some axes. We're given these labels, I think it was pi on 2, pi, and 3 pi on 2. Well, there's no scalar multiple out the front, so if you take a look at the range of inverse tan, it's from minus pi on 2 to pi on 2. And since we're shifting everything up by pi, our asymptotes are now here, so we can asymptote at x, or in fact of y, is equal to pi on 2, and y is equal to 3 pi over 2. And we have an inflection point right here, right in the middle, and we know that coordinate, we had to label this coordinate, which was 2 pi, and your inverse tan graph will look something like this. We didn't have to label intercepts because, yeah, the value here wouldn't be very nice. For question 7, we were given this piecewise function. So f of x is defined to be this linear equation if x is less than 1, and 4 over x squared plus 1 if x is greater than or equal to 1. And suppose that f and f prime are continuous, we have to show that m is equal to minus 2 and n is equal to 4. So first of all, if f is continuous, then these two must be the same point at x equals 1. So if you plug 1 into here, you're going to get 4 over 1 plus 1, which is 2. And that should be equal to m times 1 plus n. So you're plugging 1 into here. So we get your first equation, which is m plus n is equal to 2. So that's if f is continuous. And now if f prime is continuous, then the derivatives must match up at 1. So derivative of this linear equation is just m. And derivative of 4 over x squared plus 1, well, that's minus 4 over x squared plus 1 squared, and then using the chain rule, we multiply by 2x. And if you evaluate this thing at 1, we'll get 1 squared plus 1, and then 2 times 1 is just 2. So 1 plus 1, that's 2. And 4 over 2 squared is 4 over 4, which is 1. So this whole thing is 1, and then minus times 1 times 2, that's exactly minus 2. So if m is equal to minus 2, then if we look back on this equation, minus 2 plus n is equal to 2, which means that n is equal to 4. So that's how you show m and n are their respective values. For the next part of this question, we're asked to evaluate the integral from 0 to square root of 3 of our function f of x dx. And well, notice that they're different functions depending on whether you're less than 1 or greater than 1. So this is equal to the integral from 0 to 1 of mx plus n, which is minus 2x plus 4 dx, plus the integral from 1 to the square root of 3 of 4 over x squared plus 1. These aren't too bad to evaluate. This is going to give you minus x squared plus 4x evaluated from 0 to 1, and then plus 4 integral or antiderivative of x squared plus 1, that's inverse tangent of x, and we have to evaluate this from 1 to root 3. And notice if you plug 0, in fact, yes, if you plug 0 into these x's, then they all cancel out. So we plug 1 into here, which is minus 1. Plug 1 into here, that's plus 4. And then we have plus 4. Inverse tangent of root 3, that's pi on 3. And then inverse tangent of 1, that's pi on 4, so subtract pi on 4. But pi on 3 minus pi on 4, that's pi on 12. So we're left with, let's see, 3 plus 4 times pi on 12, which is equal to 3 plus pi over 3. And that's the answer. For question 8, we're given this equation y equals 2 times the square root junk, and we have to find the volume of the solid that's formed when we revolve this function around the x-axis on the interval 1 comma root 3. And this might seem intimidating at first because we have this big square root, but it's not too bad, because if you look at the volume formula, which is pi integral from these bounds, so 1 to root 3, we have y squared dx. And notice when you square your y, or you cancel out these square roots a little bit. So if you plug this in, y squared, well, we have 2 squared, which is 4, and the square root squared, which is just the thing inside, so x squared plus x plus 1 over x plus 1, x squared plus 1 dx. And we can move this 4 out to the front because it's just a constant. And now what we have to do on the inside is do partial fraction decomposition. So partial fraction decomposition on x squared plus x plus 1 over x plus 1, x squared plus 1. So notice we have some factors. So this should be equal to a over the linear factor. Plus, now since we have a quadratic factor, it's bx plus c over the quadratic factor. And now if we cross multiply, or if we multiply both sides of this equation by this big denominator, notice that if you multiply this denominator over here, x plus 1 and x plus 1 will cancel each other out, leaving us with just a times x squared plus 1. And if you multiply this big denominator on the second term, x squared plus 1 will cancel out with this denominator, leaving us with just bx plus c times the linear factor. And now let's expand things out. So this is ax squared plus a, plus now expanding this out, we get bx squared plus bx plus cx plus c. And now let's group a couple things together. So let's take a look at the x squared terms. The coefficients are a plus b x squared. For the linear terms, we have b plus c as coefficients, and for the constant term we have a plus c as a constant. And now we just have to match these coefficients up to the coefficients we have over here. So in fact a plus b should give us 1, b plus c should give us 1, and a plus c should give us 1. And this is really easy to solve, because if you have a plus b is equal to 1, then b is equal to 1 minus a, I guess. And let's see, if b is equal to 1 minus a, then if you look over here, 1 minus a, which is b, plus c is equal to 1. Which means that, well, these ones cancel out, and you get a is equal to c, but a plus c is equal to 1, so 2c equals 1, which means c equals a half, and since a equals c, we have a equals a half. And since b equals 1 minus a, well, 1 minus a half is just a half. So all these constants or coefficients are just 1/2. So what we get in the end is pi, or 4 pi, times the integral from 1 to root 3. Now a, b, and c are all 1/2, so let's factor that 1/2 out to the front. So we get 2 pi, because 4 pi times a half is 2 pi. And then we're just left with 1 for all these coefficients. So 1 over x plus 1 plus, and now let's fill up the fraction as well. We have x over x squared plus 1 plus 1 over x squared plus 1 dx. So right away I can see that this is going to give us a natural log, this is going to give us a natural log, this is going to give us arctangent. So let's see what we can do from here. So if we split up the integral, we get the integral from 1 to root 3 of 1 over x plus 1 dx plus, now notice we have x and some quadratic, x squared plus 1. Derivative of x squared plus 1 is 2x, which is pretty close to what we have. So ideally we want a 2x up here. So let's in fact force a 2x up there. But we can't just put a 2x, we have to divide by 2. So multiply by half to kind of compensate. So now we can integrate from 1 to root 3 of 2x over x squared plus 1 dx. And then we have plus the integral from 1 to root 3 of 1 over x squared plus 1 dx, like so. So evaluating these integrals are pretty easy, quite standard. So integral of 1 over x plus 1, that's a natural log of x plus 1 from 1 to root 3 plus 1/2. Now we have derivative over function, so that's going to give us natural log of the function itself, x squared plus 1 from 1 to root 3, and this is going to give us arctangent, as I said before, so plus arctangent of x evaluated from 1 to root 3. Let's rub out this working out over here, it's getting a little bit in the way. So now what can we do? Well, we just sub in the bounds and we more or less get our answer. So I actually got this interval wrong, I believe it's supposed to be from 0 to root 3, not 1 to root 3, so all these bounds should have been changed. So notice if you plug 0 into here, we get natural log of 1, which is 0, so that is irrelevant. Same thing over here, if we plug 0 into x squared, we get natural log of 1, which is 0, so that's irrelevant. And if you plug 0 into arctangent, you also get 0, which we can ignore. So now we're left with 2 pi. Now, let's see, we have, subbing in root 3 into here, we get natural log of root 3 plus 1. So natural log root 3 plus 1. Subbing in root 3 into here, we get root 3 squared plus 1, which is natural log of 4. But we also have 1/2 factor out the front, which we can bring into the exponent to turn it into natural log of 2. So this is plus natural log of 2. And then plus arctangent of pi, and plus arctangent of root 3, which is pi over 3. So plus pi over 3, like so. And now what we can do is combine these two natural logs together using natural log properties, and we get 2 pi natural log. 2 times root 3 is 2 root 3 plus 2, and then plus pi and 3, and that's the answer. They also want it in this form. They wanted it in the form 2 pi natural log of some constant plus some constant. So yeah, this form works. So question 9 was the last question on this exam, and we're given these pair of parametric equations, and the first part asks us to show that if dy dt squared was given in this form, then a must be equal to 1, b is minus 2, and c is 16. So to do this, let's first find dy dt. And this is equal to, well, differentiating y, we get 1 over 1 plus t first, and then plus 1/4, derivative of this thing is 1 over 1 minus t, but because we have this negative, we have the chain rule, so introduce a negative over here, and we have to find dy dt squared, which is just this whole thing squared, and well, this evaluates to this first term squared, which is 1 over 1 plus t squared, minus 2 times the first term times the second term, so 2 times 1/4 is minus a half, so minus 1/2. Then 1 over 1 plus t over 1 over 1 minus t. Notice we have some difference of two squares action going on, so this is equal to 1 over 1 minus t squared. And then plus the second term, but the whole thing squared. So minus a quarter squared is 1/16, and then this should be 1 over 1 minus t, but the whole thing squared. And you can clearly see that a must be 1. If you turn this negative into a plus and put it down here, then b is minus 2, and c is 16. And for the second part of this question, we have to find the length of the curve that's defined parametrically by these two equations. On the interval t, going from 0 to 1/2. So to do this, we're going to use the arc length formula. So that's the integral from 0 to 1/2. This is the arc length formula for parametric equations. So we have the square root of dx dt, but the whole thing squared, plus dy dt, but the whole thing squared dt, like so. So we know what dy dt squared was, that's why we found it over here. Let's find dx dt squared. So dx dt, or derivative of arc sine, is equal to 1 over the square root of 1 minus x squared. And if you square this, then the square root just disappears, so you're left with 1 minus, sorry, that's supposed to be t squared, so 1 minus t squared. So let's sub everything in. So we have the integral from 0 to 1/2 of the square root of, let's see, dx dt squared, we know that's 1 over 1 minus t squared, plus dy dt squared, which is 1 over 1 plus a t, but the whole thing squared, minus 1 over 2, 1 minus t squared, plus 1 over 16, 1 minus t, but the whole thing squared, all inside of this square root. And this is in fact where I made my second mistake on the exam. It was quite careless, but basically what we have to do here is simplify and notice 1 minus t squared, and we also have this 1 minus t squared. So let's combine these two. So we have one of these 1 over 1 minus t squared, and a half of these 1 over 1 minus t squared. So 1 minus half should give you a half, but for some reason I wrote down negative a half. Maybe, I don't know, I got confused by this negative sign somehow. But yeah, I ended up writing down negative a half instead of positive a half, which is what it should be. So this is supposed to evaluate to the integral from 0 to 1/2 square root. Let's write this first term first, so 1 over, and I'm actually going to write this as, let's see, 1 plus a t, but the whole thing squared, and then plus, so in the exam I accidentally wrote down a negative instead of a plus, but whatever. We have 1/2, and then 1 over, and now notice 1 minus t squared, difference of two squares, that's exactly 1 plus t, and then 1 minus t, like so, and then a plus 1 over, and I'm going to write this as 4 times 1 minus t, but the whole thing squared, like so. And the goal is to try and turn this into a perfect square, so we can cancel out with this ugly square root. And let's see where we can go now. Well, notice on this second term, 1/2, that's exactly 2 times a quarter. So this is the same thing as plus 2 times 1/4. And we can move the 1/4 into this bracket. And we can move this 1 plus t out a little bit. So let's write it like this. 1 over 1 plus t. And remember we had that quarter, so let's multiply it right in there. So hopefully you agree with everything so far. So this is 2 times this times that. And notice this factor is the same as what we have inside the square term, and this factor is the same thing as what we have in here. So in fact we have something squared plus 2 times, well, these two multiplied together, plus the latter thing squared. And this is exactly the binomial theorem, so a squared plus a 2ab plus a b squared, you can simplify this down to a plus b, but the whole thing squared. So now this is equal to the integral from 0 to 1/2 of the square root of a, which is exactly 1 over 1 plus t, so 1 over 1 plus a t, and then plus b, which is 1 over 4, 1 minus t, and then this is the whole thing squared in the square root. And the square and the square root obviously will cancel each other out, leaving us with the integral from 0 to 1/2 of 1 over 1 plus t dt, plus the integral from 0 to 1/2 of 1 over 4, 1 minus t dt. And now let's evaluate these integrals. So this is going to give us natural log of 1 plus t, evaluated from 0 to 1/2, plus the natural log of 1 minus t, evaluated from 0 to 1/2. But because of this negative, we have to use a bit of chain rule, so that should be a negative outside. And notice if you plug 0 into this t, natural log of 1 is 0, so let's ignore that. Same deal over here. And now we're left with natural log. 1 plus 1/2 is 3/2, minus, now 1 minus t, which is 1/2, so 1 minus half, which is 1/2, so natural log of 1/2, like so. And I actually forgot a quarter out the front, so let's put a quarter down. And the question actually wanted us to put it into the form natural log of a plus a b natural log of c, something like that, where a, b, and c are all rational, which they are in this case, which is quite nice. So yeah, in the actual exam I put down a plus here because of that sign mistake I made during the calculation process, but yeah, this should be a negative. If you wanted a plus here, then you would have to turn this 1/2 into a 2, but it's the same thing. So that's pretty much everything for this exam. Quite annoyed about these 2 marks, but yeah, it is what it is. And I just got to focus on tomorrow, which is exam 2. And hopefully that would be pretty fun as well. So I thank you guys for watching. I hope this video helped if you needed it. And yeah, until next time, have a wonderful day, and I'll see everyone later. Bye bye.